Welcome to my talk, detailed mathematical examination of neutron behavior. You guys aren't laughing. Okay. Many people believe that low-energy nuclear reactions do not produce neutrons because neutrons are not detected. This is an unfortunate situation, and it prevents researchers from exploring the possibilities of neutrons in LENR. For 30 years, LENR theorists have hypothesized many novel ideas without neutrons. They must explain overcoming the Coulomb barrier, maintaining a chain reaction, and the lack of high-energy gammas. Evidence of neutron transmutations. All of these must be explained. But these questions are easily answered by understanding that neutrons exist. They scatter, they react, but they are not easily detected. This presentation discusses the behavior of neutrons in an electrolytic type, palladium, deuterium, LENR. I will talk about the release, scattering, reactions, detection, generation, and transmutations. Let's consider a typical reactor, electrolytic, running in steady state at 95% loaded. The electrolyte is heavy water with lithium. The most probable reactions are the usual ones seen here. But most people don't like these reactions because of the neutrons. But let's see what these neutrons actually do. I call these two the two primary reactions. The neutrons coming out of here have 2.45 MeV initial energy. The kinetic energy of the tritium and the He3 can overcome the Coulomb barrier to react with another deuterium. I call these the two secondary reactions, shown here. The neutrons here have 14.07 MeV of initial energy. A subsequent D2 plus D2 reaction can occur and a chain reaction will ensue. Now the energy for that chain reaction comes from the previous reactions. You don't need to violate thermodynamics in order to make the reactions occur. And this is exactly the same phenomenon that occurs in a fission reaction. The neutrons scatter in the LENR apparatus, in the reactor core with the palladium and deuterium, in the electrolyte with the deuterium, the oxygen, and the lithium, in the Pyrex glass with the boron, oxygen, and silicon, and they scatter in the water bath with the H and oxygen. With each N plus deuterium scatter, the neutrons lose roughly half of their kinetic energy, and a subsequent scatter is much more likely as a result. If they scatter once, they scatter again and again. They quickly thermalize and move in Brownian motion. The mean free path of this motion is only a small fraction of a centimeter. If they do escape the apparatus, it is a rare situation, and this is examined mathematically in detail in the next several slides. Let's consider an example reactor. Let's say it's running at a relatively high excess heat. No wimpy reactions for this example calculation. I am running a big reactor and I am running it hot. Let's say these two primary reactions produce 1 watt of power. Then for that situation, I have previously calculated that the entire reactor will produce about 5 watts of heat. Like I said, I want to do a worst-case scenario here. I have previously calculated that 75% of the tritium will react with another deuterium to produce 6.48 times 10 to the 11th neutrons at 14.07 MeV. I want you to remember that number, 6.48 times 10 to the 11th. Now the interactions are both scattering and reacting. When a neutron encounters another nuclide, it may scatter or it may react. There is one probability for scattering and a separate probability for reacting. Reaction and scattering rates are summed. I have examined both as the neutrons pass through the apparatus for their first interaction. Here you see a description of the apparatus, the typical dimensions, except that the water bath is somewhat small. The entire thing has a radius of only 28.5 centimeters. That's about 11 inches. I have divided the apparatus into 4 segments: the core, the electrolyte, the Pyrex, and the water in the water bath. This is just the first half of a very large table. It's too big for one slide. The second half is on the next slide. The first row here is the scattering in the core with the palladium and the deuterium. Under that row is the reactions in the core. And the information in the columns for both the top 2 rows is the cross-section of the interaction, the distance that the average neutron travels in that particular segment, the density of the interacting isotope, and the resulting number of interactions. This is done for both deuterium and palladium. To the right of that, in the green highlighted box, is the sum of that interaction, both in percentage and in number. Under this section, highlighted in blue, is the number of neutrons that escape that segment and go on to the next segment. Below that thick black line, I calculate the number of neutrons that scatter and react in the electrolyte. There are 3 elements in the electrolyte: the deuterium, the oxygen, and the lithium. These calculations are the same as the ones above. The blue at the bottom section shows that only 39% of the original amount of neutrons did not have an interaction. They will continue through the apparatus at this 14 MeV energy. And they go into the electrolyte, they go out of the electrolyte and into the glass Pyrex beaker. But the rest of the neutrons have scattered or reacted in this first interaction. And I will consider them again in their second interaction, but let's continue on with this first interaction. Here is the second half of this very large table. The remaining neutrons that have not scattered or reacted are now in the glass of the Pyrex beaker, which is made of boron, oxygen, and silicon. As before, with the other parts of the apparatus, the neutrons scatter and react. The neutrons that exit the core, the electrolyte, and the Pyrex glass without scattering or reacting is 37.7% of the original amount. They go on to the water bath. As you can see in blue here at the bottom right, 0% escape the water bath. In other words, 0% go inside that second glass beaker surrounding the water bath for this first interaction. Furthermore, a full 19.3% of the original amount of neutrons have reacted just during this first transit through the apparatus. They are no longer neutrons in the apparatus, they've reacted. Let's do a close-up of what we see here. This is just a small section of my working spreadsheet. It's not meant to be pretty. It's what I use to work to do these calculations. Now, behind every number is a calculation. Here, you see I have selected a box with a number in it, right here. Here, you can see the calculation behind that number. Here, you see the equation behind that calculation. The cross-sections are based on experimental data from the JANUS website. First, you select the element, hydrogen. Then you select the isotope, hydrogen-2. Then you select the reaction type. For scattering, that is elastic. You see the curve here. Then you select the energy right here. I zoom into the energy and you can read the value for that reaction type. Now scattering is easy. Reactions are much harder. Many elements have numerous isotopes. For example, palladium has 6 isotopes, as shown right here, that are stable. And they occur in these natural abundances right here, respectively. At 14.07 MeV, each of these isotopes has numerous reactions with neutrons. For example, there are 7 reactions for palladium-102 at 14.07 MeV. These are the 7 reactions that occur when a palladium-102 encounters a neutron. To get the probability of a reaction, you take the reaction cross-section, which you read off that table, like I showed you. You take it times the distance that the average neutron will travel, times the density of that particular nuclide, or I should say isotope. Then that gives you the probability for one reaction. So the probability for one isotope is the sum for each reaction for that isotope. And the probability for one element would be the weighted average of that isotope times the abundance of that. I'm sorry, it's the weighted average. Let's go back and look more closely at the bottom results in Table 1. Here, you can see this is the percent that scatter in the water bath for the first interaction. It's 254%. Well over 100% will scatter at this energy. What does that mean? It means I could cut that size of that water bath in half, and I would still get over 100% of those neutrons would scatter. Let's look at this. 0 neutrons escape without scattering. And here you see of the original amount, I have 19.3 that react. They are no longer in the apparatus. Now let's look at the second interaction. I'm going to show you a summary table of that. Here's the summary. For the second interaction, 10 more tables were created, similar to what you saw in Table 1. And that's because there are 10 different neutron amounts and initial energies depending on from what they scattered and from where they scattered. Here I have where they scattered from, their energies, the number of neutrons in that situation, and these are the number that scattered in that second interaction, and here are the numbers that react in that second interaction. I've summed them right here. I've got some interesting numbers here, but let's skip down to this one. The total percent of neutrons that have reacted after only 2 interactions is 79% have reacted. That's a pretty high number. Now these are real numbers. Each number has a detailed mathematical calculation behind it. With each of the initial energies for Table 2, the cross-sections had to be recalculated for each reaction of each isotope for each element. I want you to know that's not an easy task. Now these are my working tables that I'm going to show you. They're not meant to be pretty, they're meant to be useful. I have shrunk down 10 working tables so you can see the entirety table on one page. Now inside each tiny box, here's a little tiny box, this thing here. Inside each tiny box, it represents a calculation. Here you can see the calculation represented by that number. The next few slides show the 9 other working tables that were used to get this summary table. And I've shrunk them down so you can see them all on one page. And like I said, these tables are difficult to create. It takes a couple of days for each table. Obviously, there are too many numbers for you to see, much less the calculations behind these numbers. The point of showing you these 10 very large tables is to show you that these numbers are real. My calculations are real, and my conclusions are real. Anyone calling these calculations as being my imagination or fantasy is simply incorrect, Before anyone claims that my calculations are incorrect, let them first do this exact same calculation, this exact same detailed mathematical analysis, and then try to claim that these numbers are wrong. Anyone who would like to see these detailed working files is welcome, just ask. But we are only halfway done through this analysis. So far, the neutrons have scattered only twice, and yet 79% of them have reacted, and well over 100% have scattered. As the neutrons slow, their scattering and reaction rates are determined to calculate how many neutrons are left in the apparatus. I'm going to go from 2.5 mega eV down to 100 milli eV. For every energy, the reaction cross-sections must be redetermined. Here are the 9 more tables, and a summary will follow. As you can see in these tables, I start with 2.5 MeV, and I go to 1 MeV, and then I go down by factors of 10 for each table until I get to 100 milli eV. I want you to know these tables are not easy to construct. Each table takes several days' worth of work to create. And this is not a simple math problem that you can scribble out on the back of a napkin. It's not something you can toss into a computer and let it crank. These graphs and numbers have to be examined, determined, and calculated for these 20 tables that you have just seen. Here's a summary of the cool-down interactions. The first column is the interaction number, and I take it out to only 28 interactions, as you can see here. The next column shows the energy range. This is the amount of neutrons in each of those energy ranges and how many interactions they will have in that energy range before they shift down to the next one. Column E here is the number of neutrons still in the apparatus after that interaction. Column F is the percentage. Now, column G is the percentage that do not react, again related to the initial amount. Column H is the percentage of neutrons that remain in the apparatus, and this is relative to the original amount. You remember that that was 6.48 times 10 to the 11th. Again, you see there are no neutrons that remain in the apparatus, none. Let's read this green box here. The neutrons have not reached room temperature of 26 MeV, and yet they have all reacted. None of the neutrons ever reach that second borosilicate glass container surrounding the water bath. Any maverick neutron that might reach that second borosilicate glass will most likely react with the boron or the oxygen in there. Let's look at column I here. This is the mean free path of the neutrons as they interact with the hydrogen one in the water bath. As you can see with these numbers here, for most of the interactions, after the first 2 or 3, the neutrons barely make it more than a small fraction of a centimeter. They just sit there vibrating back and forth, stuck in the water, until they eventually react. After 28 back and forth scattering interactions, they have all reacted. Next, I show some graphs of this, the number of neutrons that are in the reactor versus the number of interactions. And this is the mean free path in the water bath. As you can see, for most of the time, it just sits there in a very small fraction of a centimeter, just sitting there vibrating. Now, I did not have to include the glass of that water bath because the neutrons never reach it. If a maverick neutron ever did escape the apparatus, how would we detect it? Let's look at that next. Neutron detection. Commercial neutron detectors must be used. They are costly and, as a result, not often used in LENR experiments. Let me tell you, gold coins do not work. Please do not use a gold coin and think that you're going to be detecting any neutrons. Neutrons must be moderated first in order to be detected, and that is done by passing them through polyethylene. For my example apparatus, with the dimensions of it, I calculate that I get, for every neutron that gets emitted, I only detect 1 out of 900. Now, after a neutron goes in, that's the number that go into the detector. That's not what I detect. That's the number that enter the detector. Thank you. After the neutron enters the detected, it needs to be counted. Now, the count is not the number that enter that tube. Rather, it is proportional to that number, and it has a huge reduction factor. It's estimated, I did an estimate, it's estimated to be about 1 over 64, or 1 over essentially infinity. In other words, you need to calibrate it. The important point is that one count does not represent one emitted neutron. Regarding the number of counts compared to the number of neutrons actually entering the tube, that constant of proportionality is very large and quite variable. I've made some estimates. The energy of the neutron must be consistent with the length of the tube. You see, the tubes come in various shapes and lengths. The energy of the neutron must be consistent with the length of the tube. If the length is well matched, then about 1 out of 64 will be detected. That is the best case. If the tube is much too long, the neutrons will get stuck in the moderator, just like they got stuck in the water. If the tube is too short, the neutrons won't get moderated enough and they just blow right past the He3 gas chamber without reacting. Neutron detection. How many mavericks are there? We talked about the average neutrons, but what about these mavericks? I've made some what I call reasonable and fair estimates of standard deviations to estimate the number of maverick neutrons that may come out of the reactor. An example reactor running with a neutron production of 0.6 trillion neutrons per second, that's what I was doing. Of these, I estimate only about 10 neutrons per second would be detected. Now, a count is not the same coming out of a detector as the number that are detected. The difference between a count and how many were detected depends on the sensitivity of the electronics, and it must be calibrated using a neutron generator. How much time?
Yeah, 1 more.
1 more minute? All right, okay. Let's talk about neutron generation. How do you generate neutrons? Well, you take a metal that absorbs deuterium and you load it up to a moderate density. Then you use a linear particle accelerator and bombard that metal sample with either tritium or deuterium, and that overcomes the Coulomb barrier to react with the deuterons. The two reactions that occur are the same ones that I showed you previously. The charged particles are stopped in the metal, but the neutrons are ejected from the metal with 2.45 MeV. If you're using tritium, then you get this amount, 14.07 MeV. If you want to check on neutron generation, look it up on Wikipedia. I'm going to read some of this in yellow. Fusion of deuterium atoms results in the formation of helium-3 and a neutron with a kinetic energy of approximately 2.5 MeV. Fission of a deuterium and a tritium results in a helium-4 with an approximate energy of 14.1 MeV. The basic concept was first developed by Ernest Rutherford in the early 1930s. This was the first demonstration of nuclear fusion, as well as the discovery of helium-3 and tritium. While neutrons generators do produce fusion reactions, the number of accelerated ions is far too low for ignition to be maintained. There is no net fusion power. Now, you have probably noticed already this is remarkably similar to LENR with one difference, the maintenance of the chain reaction. That compact linear accelerator is not needed. Now, low energy fusion has been known since the 1930s. It's the chain reaction that we discovered in 1989. So don't let any skeptic tell you that LENR is not possible, because scientists have been performing low energy nuclear reactions for over 90 years. It's the chain reaction that is new since 1989. Let's have some definitions here. Hot fusion requires 100 million degrees K. Cold fusion does not. For over 30 years, we've been saying that there must be two different things because we misunderstood neutrons, but neutrons exist in LENR. So the reactions for neutron generation are the same as in LENR. We don't need some kind of new novel physics. What is the evidence of LENR in reactions? Carbon. Well, we have experimentally observed carbon, ENG8, it is this reaction right here. Silver, we've observed silver. It's this reaction right here. And we just saw Kumar observed copper. It is a similar reaction to this if we get copper 65. I'm almost ready to conclude. Okay, here's some more evidence of nuclear reactions. No neutrons has been widely believed. It's the general consensus, but it's been perpetuated by the idea that there are no neutrons detected, therefore there must be none created. But this is a misguided and ill-conceived idea. Rather, let's explore the possibilities. For over 30 years, the general consensus has been there is no agreement. Let's get rid of that forbidden region, and we might find a more unified answer. What might we learn? Any questions, please?
Question here. Oh, change.
Sven.
Hello. Yeah. I have a neutron source in my lab who's giving about 5 giga neutrons.
5 gigaamp?
5 giga neutrons per second.
Okay.
So I have a detector 2 meters away from it, and I see neutrons. I was just estimating that 1 in 1,000 reaches the detector.
Okay, so 1 out of 1,000,
yeah.
right? Yeah,
Yeah.
and that's because it depends on the length of the tube and the sensitivity of the electronics after it gets detected.
Yeah, but this is
Right.
a distribution of, say, 0 up to 7 MeV neutrons.
Okay,
So it means that you would need something lower than 1 MeV neutrons to not see anything. The numbers you have, I don't know. But
well, the moderator, I would guess that your neutron detector has a moderator in it. I don't know, but I would guess that.
It's actually the source is wrapped in plastic and boron.
Okay,
But still,
right.
you get it out.
You get some, yes.
yeah.
But you can't, just because a neutron gets counted, that doesn't mean that's how many neutrons were detected or were emitted, as you're saying.
Yeah.
Yeah, okay, thank you.
Okay, maybe one last question, because after that you will be punished and no coffee break.
Yes.
Hi, Lynn. Thanks for the talk. My question is, so there have been reports of sort of conventional energy neutrons, for example, Jones in 1989. It's not working. For example, in 1989, when Jones reported in Nature, when Jones reported in Nature 2 to 5 MeV neutrons, I think that's likely canonical DD fusion neutrons.
Right.
And so, but in most of the experiments, basically the detection of those low-level DD neutrons are sort of anti-correlated with excess heat. Jones didn't see excess heat. So in some sense, the production of, I don't doubt that there are low-level production of DD neutrons in certain experiments, and I think that there's compelling reasons for why that is, and we can talk about that later. But those observations are anti-correlated with excess heat, and secondarily, if excess heat did have the commensurate amount of neutrons, and shouldn't you also, and let's say, even if they did, none of them did escape, and they were all stopped in the reactor, you should see gammas, for example, from the neutron stopping reaction,
Right.
shouldn't you?
Let me go back to this slide that I skipped over so quickly. Several experiments have detections of low-intensity, low-energy gammas, and this is evidence of neutron absorption, especially in the water. The predictions of the helium-4 to heat ratio, when you consider both the primary and secondary and the tertiary reactions, it's right on target. It's exactly on target. Yeah.
Okay, I think we have to stop, because otherwise we will have no lunch and no coffee.
We'll
That's
discuss
right.
it. We'll
Let's
discuss it out there.
let's discuss the
All right,
coffee break.
thank you, everyone.
Okay, thank you again.